Hello. In the last class, we looked at how the PN junction interacts with incoming radiation. So, we have a PN junction based solar cell which is our typical photovoltaic solar cell, and then you have incoming radiation. We looked at what happens across the boundary. We looked at how the charges are charge carriers are created on each side of the boundary, and the fact that because there is a boundary, because there is a depletion region or a space charge region, and because there is band bending, the negative charges accumulate to one side, the positive charges accumulate to the other side, and that is how you have the charge separation, and therefore you have some stabilization of the charges, and then you are in a position to tap it for electricity outside. We also understood the fact that this is a PN junction, it is functioning as a diode, and so if you have the charges appropriately positioned, you have excess positive charges on the P side and excess negative charges on the N side, then you have automatically forward biased the diode, and this does not have to be necessarily using a battery in an external circuit. Even internally, due to incoming solar radiation, when you do that, you create a forward biased PN junction, and therefore that has some characteristics associated with it. So, in this context, we also looked at circuit elements that describe what is happening with respect to PN junction when you attach a load to it, a PN junction based solar cell. When you attach a load to it, what are all the various components that sort of show up in that circuit, and what are they representing, how the current flows, etc. We had some diagrams that we put up. So, from there we will take it a little forward here. In this class, we are going to look at the solar cell characteristics and usage sort of from an external circuit perspective. We looked at it only as a PN junction previously. Now, we will take that, I mean fundamentally it is a PN junction, so those characteristics are going to be there. So, we are going to try and see what we can understand in terms of given that these are the characteristics of the inherent junction, what are you likely to see in the external circuit, and what are some ideas associated with that. So, that is the point that we are going to see, and that is what I mean by saying solar cell characteristics and usage. In terms of usage also, how those characteristics, because that is what the external circuit says. So, we have to understand in terms of usage what are the implications. So, our learning objectives are to determine the operational characteristics of a PN junction based solar cell, which is what, as I said, is how the solar cell will behave with respect to an external circuit. So, once an external circuit is hooked up to it, what is the behavior that the cell will display towards it, what can the external circuit expect out of it. So, that is one important thing that we are going to look at. And once you understand that, we are also going to look at using that information, using that understanding, we are going to see what is the best way to use the solar cell. We are going to look at what is the best way to use the solar cell, because the solar cell has some characteristics, and as you are going to see in this class, if you ignore those characteristics, you could use the cell in a very poor way, very ineffective way, and as a result you will not get the full benefit of the solar cell. So, you have to be conscious of those characteristics, and only then you can make the best use of the solar cell, and you have to keep that in mind both in terms of when you buy the solar cell, what to expect from it, when you use the solar cell, what to expect from it, how do you compare solar cells that are available. All those things are intricately related to this idea that it has some characteristics, and you need to know those characteristics to characteristics meaning its behavior, when how much current it will give, at what voltage it will give, that is what I am referring to as its characteristic. So, as the voltage changes, the current changes, and so there is some graph that comes out of it. So, you have to know that. Only then using that plot for different solar cells, you can compare them. You can compare this as a function of time as the solar cell ages, and also what is going to happen to that characteristic as the sun moves. So, let us say you have a bright sunny day, you are going to see some behavior, a cloud goes on top of it for some period of time on top of the solar cell, and therefore blocks the sunlight a little bit. So, there is going to be a drop in intensity of the sunlight. So, then naturally the the behavior of the solar cell is going to change. So, how do you understand that behavior, and therefore how do you keep that also in mind when you operate the solar cell. So, these are the kinds of things that we are going to look at when I say what is the best way to use the solar cell. Okay. So, these are the operational parameters that we are going to look at in this class. Okay, so as we already plotted once in one of our earlier classes, we looked at this plot. This is the current voltage characteristic of a diode, and so you can see that this is the forward bias, and this is the reverse bias. As we discussed in the forward bias, we reduce the space charge region or the depletion region, and then pretty soon the current starts flowing. So, for up to some voltage you are fighting the a voltage that was inbuilt in the system, and then eventually you overcome it and then you start flowing current, and so after some point you see a steady increase in current. So, this is what you see. In the reverse direction, you have a very small reverse saturation current which is almost negligible in the scale, you do not see it here, and then from there on you basically have you keep building potential in the negative direction. It keeps growing the space charge region, and therefore becoming more and more of resistor, or more and more of a blockage to the flow of current, and then eventually this material breaks down, and then you have this sort of breakdown voltage, after which you see very high current, but that is not really the mode in which we want to typically operate this diode. So, if you want to for the purpose of this class, we are going to look at some equations, and the main thing that we need to look at here is this equation that you see up here, which relates the diode current ID to the diode voltage that is shown here. Okay. So, diode current to the diode voltage is the relationship. This may look a little complicated, but actually we are not going to derive this. If you actually look at semiconductor textbooks, they derive this. Primarily to derive this, they are looking at how the charge carriers are created, how the charge carriers move from one side to the other, and from the other side to this side, the majority charge carriers, minority charge carriers, what role are they playing, all of that is looked at, and based on that you come up with this idea of what is the current when you have some amount of voltage. Now, you will see here there is an I naught, this is the reverse saturation current, the small value that you will see somewhere out here, it is a reverse saturation current, and you see here some parameters. So, you have Q, that is the charge on the electron, the Vd is the voltage on the diode, so that is what we have there, and K of course is Boltzmann's constant, T is the absolute temperature. So, in fact we even talk of this you see this Kt by Q or Q by Kt that is listed here, but if you write it as Kt by Q, that is referred to as a thermal voltage. Okay. So, you have a parameter like that which we will we are not really deeply interested in that, and one constant here gamma, in different books they call it gamma, eta, n and so on, which deals with ideality or non-ideality of this system. Usually gamma has values between 1 and 2, 1 to 2. So, that is sort of the number that we are looking at for gamma. It is something representing how ideal or non-ideal the system is. In fact, it relates to all the discussion that we had on direct bandgap semiconductors, indirect bandgap semiconductors and so on. So, there are some terms out here, and actually this whole exponential part, the fact that you have an e power something. So, e power e power something you are having, right. So, this e power something comes from the equation for the charge carrier concentration. So, the behavior of the charge carrier concentration is what results in this e power something, and that is how eventually when you have to you need these charge carriers to do the current to carry the current, so to speak, and therefore in the current equation some term corresponding to the charge carriers is going to show up, and therefore you end up having this exponential term that you see out here. Okay. So, that is how that exponential term ends up arriving. So, we find that ID is related to the current in the diode is related to the voltage of this diode using this equation that you have here, where you have an e power some constant. So, you can call Q by gamma Kt is all constant, all these are constant once you set the temperature, to be something, then Q by gamma Kt is a constant. So, you essentially have you can even write this as ID equals I naught e power some constant let us say A Vd minus 1. Okay. Minus 1. So, A V subscript D. Okay, so A, B, D subscript V subscript D minus 1. So, this is basically what we have. In our subsequent equations, I will still keep the Q by gamma kT available, but you just have to keep in mind that it's simply it is not as complicated as it looks on the once you write all the terms, but because it's all several of them clubbed together as a constant, and so that's just something that you have to keep in mind. Okay, so this is the relationship of ID to the VD. So this relationship we will use to understand how the solar cell behaves as you attach some kind of an external circuit to it. So if you go here in this page we have a bunch of equations. I will walk you through them, so there is nothing to worry about. The primary equation is what you saw here. So let me just clear some of this so it is clear to you. So the primary equation is what you see out here, which is how the ID relates to VD. So just keep that in mind, and I am going to show that again in the next slide. And so even though there are several terms, in fact it is just some simplification of a set of terms which includes this particular term of ID, which is the diode current. Okay. So now we saw in our previous class the equivalent circuit. So I will just walk you through the equivalent circuit and then go through these equations so that we understand what is the various parameters and how they relate to this equivalent circuit. So on the equivalent circuit you see this, this is where your solar cell is sitting, and that is creating this photocurrent. So there is a lot of light falling on it, photocurrent is being created. So this is the direction of conventional current. So you have positive charges heading off that way, and this is the so this is the same diode in so you have positive this side and you have negative this side, and clearly this the internally it is a diode, internally as I said it is a diode, and so when you build up more positive charges on the P side and more negative charges on the N side, you have internally forward biased the diode. So this is that diode that we are talking of, internal to the solar cell. So this is not an external circuit, this is internal to the solar cell, right. So this is a forward biased diode, and so some amount of current will flow through the forward biased diode and internally get consumed. We do not want that to happen, but that is what is going to happen. So some will always happen that way, okay. So that is going to happen. Then we also saw that if you generate all these charge carriers, there is always going to be some recombination that is occurring, okay. So that is internally again sort of an internal shunt resistor that we are putting here, which basically means this you are getting a opportunity for those electrons and holes to recombine within the solar cell, okay. And when it recombines, that is again some current that you cannot get in the external circuit because you have lost that charge carrier. You created the charge carrier, and so it shows up as part of your photo current that you generated, but you lose it before you get to the external circuit, it is consumed internally. And then you come to the finally you manage, once you get past these two processes, you get some current out into the external system. So when you get the current out to the external system, it has to anyway go through the internal processes and arrive out of the circuit. So the current flows through a solid some solid region, physical region through which the current flows, right. So corresponding to that there is some resistance. So even within the cell there is some internal resistance that it has to flow through and then come out. So that is this resistance in series, okay. So in a sense that is also internal to the cell. So internal to the cell you can also include contact resistance, whatever. So all that is included in that. So when you get past this point only, you are actually reaching the external circuit, okay. So you get past that point, you reach the external circuit. So essentially you can say the external circuit is here, between here and here. So this side is your external circuit, this side is your external circuit. So so this is how the, so and we are saying there is some load resistor out here, and that is your external circuit. So this is how the various parts of the solar cell internally operating in their own natural ways contribute various components to the circuit, which then is operational within the solar cell, and then after you cross this internal circuit you arrive at the external circuit, which is your RL, load resistor, right. So that is why this is called like an equivalent circuit of whatever the solar cell is. Solar cell, you look at it, you do not immediately see physically a resistor there, you do not physically see a diode separately sitting there. If you put all of them together, you will sort of see this, but you recognize that there internally all these things are happening, and then you can put the circuit together. So that is what it is. So this is how you get this circuit to work. So, now let us look at a few parameters here. Let us look at the first equation. So, as I said, in fact most of the equations, even though you have a page full of equations here, as I walk you through, you will find most of them are actually quite straightforward. The only equation that may not immediately is something that you have to look at little bit more is the actual relationship between ID and VD, which we saw in the previous slide. So, beyond that most of it will be fairly straightforward, but we will still walk you through, I will walk you through the process that is happening here. So, you have I photo current that is coming here, and then we have some, so this is IPH, that is what you have here. So, coming out here is IPH. Okay, so that is what has come off the solar cell as a result of the charges, sunlight falling on it. Now, from there some current goes into this I diode. Okay, so some current goes there, right. So, what is the remaining current? The remaining current that is coming here is simply IPH minus I diode, right, simple, straightforward. So, you had IPH start off, I diode went off into the through the diode which is internal to the solar cell, and then the remaining current headed out in the external circuit towards the external circuit, which is IPH minus I diode. Let us assume we have a very good solar cell, and so at least to some degree, to simplify our calculation, we can take it into account, but we will at this moment we will neglect it. We will assume that the recombination current is very low, or in other words this shunt resistor is very high. Okay, and then in a new cell you can maybe assume that is a reasonable assumption. Temporarily we will assume that is the case. We will in fact include it later, but for the moment we will ignore it. So, we will ignore that there is any shunt resistor here. So, this is the current that starts moving this way, right. So, now if you look at your load resistor here, the current that comes here we are calling as IL, the current that is going through the load resistor. So, the first equation is simply that this IL is basically this IPH minus ID. So, this IL is whatever is coming from the solar cell, and that what is coming from the solar cell is the photo current minus the diode current. So, that is your first equation, IL equals IPH minus ID, or IPH minus ID equals IL, the way I have written it. The second equation we have here is what I showed you in the previous slide. It is simply an equation which relates the diode voltage to the diode current. Okay, so, that is all that equation is, it relates diode voltage to diode current. As I told you, that comes from the basic behavior of the charge carriers inside the inside the semiconductors, and how they move across the junction, what is the flux going one way, what is the flux going the other way, etc. And then once you do all that calculation, you will arrive at that equation. So, that is that equation which we are not deriving, which as I said you can look up in a book associated with semiconductors, but that is the one equation you have to look at. So, now if you look at it, what we can do is we can substitute this equation into this here. Okay, so, I have an expression for ID, I am going to substitute it in equation 1, which is let me call this equation 1. So, I am basically going to substitute equation 2 in equation 1 and do a little bit of rearrangement. Okay, so, a little bit of rearrangement. So, so that we can put something together. So, let us just substitute it there and then we will take a look. So, if I want to write it in terms of say let us say IL, okay, ID is we are put this equation down. So, I will just put that down there, IPH minus I naught e power QVD by gamma KT minus 1 equals IL. Okay. So, that is the thing we want to do. So, let me do some rearrangement here. If I want an expression for the diode voltage, okay. So, in terms of the currents that are out here, supposing I want an expression for the diode voltage in terms of the currents that are present here. So, what would I have to do? I will rearrange this. So, we have IPH minus IL. So, I am just moving the IL to this side and moving the other current to the other side equals I naught e to the power q v d by KT gamma KT minus 1. Okay. So, I have just rearranged. So, now I will move the I naught this side and I will move the 1 also to the other. So, I will basically do that here IPH minus IL by I naught, and then I can so this is now one term, and then I can move the 1 to this side. So, that will become a plus 1 equals e power q V d by gamma k t. Okay. So, now if you take a natural logarithm on both sides, so you basically and then do a little bit of rearrangement, you will get V d equals, so I will take the natural log here. So, I will put here ln of IPH minus IL by I naught plus 1. Okay. And this q and this would have been a q by gamma k t would have been there next to this. So, here you would have had this q by gamma k t sitting here. So, I will shift that to the other side. So, I will have gamma k t by q. Okay. So, I have just, so therefore, we have got an expression for the diode voltage in terms of the currents that are present. Okay. So, that is the other one equation that we have arrived at simply by looking at how by simply substituting equation 2 in equation 1, which is simply the expression for how the diode current varies as a function of diode voltage, into expression 1, which talks of how the current is distributing as it comes off the solar cell into either the load circuit or into the diode that is internally present within the circuit. So, once you do that in terms of the current, so now we only have the load current, the photo current and I naught that are present there, and with respect to that we have an expression for V d. So, this is what we have put together. Now, let us look at equation 3. So, what is equation 3? We are simply saying that there is a voltage across this diode. Okay. So, that voltage is this voltage V d. So, that voltage is this from here to here, what voltage you see is the voltage V d. The voltage that you see here across the load resistor, the voltage that you see here is V load, V subscript L, that is the load resistor, right, and so the voltage across the load resistor is V L. So, how do V d and V L relate? We just had a relationship between I d and I L, right. We came up with this equation 1, which was a relationship between I d and I L, which says that you have so much photo current, something went into the diode, remaining current goes into the load. Similarly, we can think of a relationship between the voltage across the diode and the voltage across the load. What is the relationship? Whatever is there across the diode will be equal to the load, because that is the source from where the that is where the current is generating, that will be equal to whatever is there across the load plus the IR drop across this resistor RS, right. This resistor is series resistor due to all the internal resistances present in the diode and the contact resistances. So, if you include all that, that is the resistor there. So, the IR drop across it is a voltage drop. Okay. So, you have generated a diode voltage, but some of the due to the current going through the series resistor, there is an IR drop, the remaining voltage goes to the load. Okay. So, what is this I? This I is the same I that is coming here. This is the same as in this circuit, you only have I L. Once you cross this point, you only have I L. So, this is actually I L. I subscript L is the current. It is not just some I, it is I subscript L. It is the current that is going into the load. It is also the current that is going into the series resistor, I subscript L, and the resistance there is this series resistor RS. So, therefore, the voltage of the on the load plus the ILRS together will equal the voltage across the diode. So, that is what we have here, the voltage across the diode is equal to the voltage across the load plus the IR drop that was there on that series resistor. Okay. So, V d equals V L plus ILRS. So, now what we are simply going to do is we are going to rearrange this. So, we are simply going to say therefore, V L equals V d minus I L R S. So, this is what we are going to, we are simply rearranging that equation, and for Vd we have an expression here, right, we have an expression here for Vd. So, that Vd I am going to substitute there. So, that is exactly what we have done in this equation here, which is the equation 4 if you want. So, what have we done? VL is still here, as you can see, whatever this VL is the same VL that shows up here. For Vd I have put in this expression out here, you can see the same thing here, gamma kt and then q the denominator, natural log, and then IPH, IL, I naught, which is exactly what you see in the equation that we have derived below, plus 1. Okay. So, that is the so we have basically got all the terms there, right. So, so that is Vd, the diode voltage, and this is the IR drop, which is the same as this term here, fine. So, now this is the equation which relates the load voltage to the parameters that you see, which is the load current for example, and most of the other things basically being constants. So, that is essentially what we do. Now, in many of the sources that we buy, we are interested in knowing what is the open circuit voltage, right. Open circuit voltage is something that we typically associate as a parameter that we should check. So, I am going to caution you here that in a solar cell there is an open circuit voltage, but as you are going to see as we go forward that that is not the best parameter to follow. Okay. So, keep that in mind that it is not going to be the best parameter to follow, but at the same time there is an open circuit voltage and we need to know what it is. Okay. So, and it is of interest to know what it is. So, in this equation 4, basically if you want to find out what is the open circuit voltage, the main thing that you have to do is to set the load current to 0. It means there is no load, right. So, you remove this entire RL, you remove RL, so it is open. So, therefore, since it is open, there is no RL there, the circuit is not complete there. So, there is no question of an IL going into that circuit, right, because there is nothing there, it is just open. So, if you set IL equal to 0, whatever voltage you get as the voltage across the load will then essentially be the open circuit voltage. So, whatever voltage becomes available at that point is the open circuit voltage. So, if you set IL equal to 0, then this term drops to 0, ILRS drops to 0, and this IL also drops to 0, right. So, if you just do those two things, you will arrive at equation 5. This is exactly the same thing, this is open circuit voltage here, you see this gamma kt by q sitting here, the natural log of IPH by I naught, because IL has dropped to 0, plus 1, and that is all there is, there is no other term here. So, this is the open circuit voltage. Okay. Similarly, we can also see that you can write similar equation for the currents. Okay. So, now let us say we also assume that there is a shunt current, there is a small amount of current that goes through the shunt. So, we have what we have actually the load current, whatever comes off as the load current will be, we previously looked at only IPH minus ID, we can also consider this ISH, the shunt current. So, if you subtract the diode current as well as the shunt current from the photo current, you will arrive at IL, right. So, that is really all you have to do, and to do that the IPH is whatever it is, right, and for the I diode we look at equation 2. Equation 2 has the I diode, except that for the V diode I am just elaborating the V diode in terms of the load versus we are going to use equation 3 in fact for the V diode, instead of just putting V diode here, for V diode I am going to put equation 3. So, that is why you see that here instead of q Vd by gamma kt I have q times VL plus ILRS by gamma kt. So, that is the additional detail that is there, and then minus 1, which is the same as in equation 2, and then the shunt current is simply whatever is there on the load. So, basically for the shunt current we simply want IRSH. So, we will simply say that the shunt current IRSH, I mean sorry ISH is simply the V on the shunt on the shunt by the R of the shunt, right. That is all you need to know, that you have a voltage across the shunt, you have a resistor corresponding to the shunt. So, V by R is your shunt resistor. So, what is the voltage across the shunt? it is simply the voltage that is there between this point and this point, right, that is the voltage across the shunt. So, what is that voltage? That is simply the voltage across the load plus this ILRS, that is the same as the shunt. So, that is what you see in the numerator here, VL plus ILRS. Okay. So, this is the relationship. So, now what we see here is that you have an equation at the bottom, which relates the in which you see this IL and you also see the VL. Okay. So, the only issue is that you see IL in multiple places. So, you see IL here also, you see IL here also, you see the VL also in multiple places. I already showed you one place, you see it here also. So, in other words, it is a kind of a complicated relationship between the load across the voltage and the current that is going, sorry, the load across the voltage across the load, I am sorry, so the voltage across the load and the current going through the load. So, it is a complicated relationship between these two, and that is what is being shown by this equation. It was very straightforward derivation. We simply looked at various paths the current takes and we have arrived at this expression. But this expression shows that the relationship is kind of complicated. It is not a simple straight line of some constant times current is not some constant times voltage, or voltage is not some constant times current. So, it is nothing like a resistor. You see here some complicated relationship where the current has in the equation for the current you also have the current value, you also have the voltage value, etc. So, it is a complicated equation. You have to use some mathematical methods to actually plot this out if you want to look at various values. You can also do this experimentally, and then you can experimentally measure current at various load current at various load voltages and make a plot. But in any case, you can take this equation. This is the equation that now describes what is, if you attach some load to the solar cell, what is the current you will see and what will be the voltage that the load will face. Okay, so and that is what typically any external unit that you are attaching to the solar cell needs to know. Right. So, you are attaching some external unit to the solar cell, that external unit needs to know that this is the behavior that is going to come from the solar cell, and therefore, you have to make sure that that external unit that you are attaching, which could be a bulb, it could be a motor, it could be a fan, whatever it is that you are attaching to the solar cell can work properly given that this is the current voltage relationship that is going to come from the solar cell. Okay. So, therefore, it is important to know how this plot looks. So, if you plot this equation, you will get a behavior that looks like this. So, if you see here, this is origin 0 comma 0. So, if you look at it, when the voltage is 0, when you set the voltage equal to 0, then basically you have short circuited the diode, right. So, that is the short circuit current. So, that is what is called ISC, and then when you basically set the current to 0. So, which means there is no current coming out of that cell, then you get the open circuit voltage, V open circuit. So, that is I short circuit and this is V open circuit. Okay, so, and you can see that this curve that you see here, it is not linear in any sense, but it is corresponding to that last equation that we had down here. So, let me just call this equation 6 for example. So, I just list that here as equation 6. So, sort of a plot of this equation 6 is what you are seeing here. Which could also be obtained experimentally. You simply have to put it together and measure all these things and do it. So, there are some experiments which do that. So, you get this thing. So, now please remember, so this is what the external circuit can see from the solar cell. Now, you should also keep in mind that any time you are trying to use some power supply to do some work, I mean to get something done, what do we have? Power is given to us in watts, right. So, power is in watts, and watts is simply joules per second. Okay, so, this is V into I. Okay, so, in joules per second. So, if you want to look at the work done equals power into time. Okay, so, I will just say V into I into T. Okay, so, V into I into time. So, that is the work that is done. So, anytime you are using some power source to get some work done, you basically want to do as much work as possible, right. So, you want to do as much work as possible because that is the whole point. You have some power source, you have something coming out of it, you want to use the capability of that power source to do as much work as possible, and that is when you have utilized it properly, utilized it efficiently, and you are not wasting resources, so to speak. So therefore, it does not help if you are taking a power source and using it under conditions where its voltage is high but current is extremely low, or current is high, voltage is extremely low, things like that. When you do all that, given that the power source has a variation in voltage current characteristic, you can select different operating points on that system. So even here, for example, I can select this as an operating point, I can select this as an operating point. If I select this point as an operating point, the voltage is high, so V is high, I is low. Here I is high, V is low, right. So with the same behavior, same cell, I can select two operating points, I can select multiple operating points. I am just giving you examples of two of them. In one case voltage is high, current is low, the other case current is high, voltage is low. In both these cases, the work that I am going to do is going to be less than the maximum amount of work that this unit can do. So when I select these kinds of operating points, when I attach some device to the solar cell that is actually at these operating points, then I am not making the best use of the solar cell. I am using it very ineffectively. So in fact, you want to keep changing, you want to pick a voltage and current location which maximizes the power that you can pick out of the cell, and therefore maximizes the amount of work that you can do with the cell at any given point in time. So if you just do all the calculation, you will find that there will be some point here. If you do all the different possible ways of getting your V and I, you will find some point there based on you have to just optimize it, and you will get one particular point here where your V and V as well as I are both high, such that V into I is a maximum. Okay. So this point is called maximum power point, or it is called, in short, it is called MPP. So this is the maximum power point, and it is important to know that such a thing exists for a solar cell, and therefore we have to use the solar cell such that we operate as close to this point as possible, so that we get the best out of the solar cell, best of whatever the solar cell is delivering to us, right. So this is what we would like to do. So we have to match the end use to the solar cell, so that we are actually able to do this. So just to highlight some of the ideas associated with this plot itself, if you just look at this maximum power point thing, I am just indicating that here. So you have something called the maximum power point, which in this case I have indicated here, and we can relate that to the hypothetical product of the maximum current you are getting there, which is the short circuit current, and the maximum voltage you are getting there, which is the open circuit voltage. So that is what is there in the denominator. So the maximum current that you can possibly get out of the system, maximum voltage you can possibly get out of the system, that is in the denominator, whereas what you actually operationally get as your best operating point is this MPP that is listed here. So maximum voltage, the voltage corresponding to the maximum power point, and the current corresponding to the maximum power point. So if you do this ratio of the maximum power that you will get from this cell in the actual operational condition versus this sort of the theoretical limit that you can consider for it, so to speak, we are referring to that as the fill factor. Okay, so the fill factor is simply the ratio of VMPP into IMPP to the product of VOC times I short circuit current. So this is a very important characteristic of a solar cell when you try to put it to some end use. So therefore it is very important to be aware of it and to actually utilize it. So I am also going to show you how we utilize it, or how we keep in mind that this is something that needs to be addressed, or even how it impacts us as you look at it. So for example, if you keep this in mind and we now look at, let us say, different solar panels. Okay, so for different solar panels, this IV characteristic could be totally different. Okay, so for example, I am showing you 3 different panels. This is panel 1, this is panel 2, and this is panel 3. So it is very important to remember that the fill factor for these 3 panels is dramatically different. So, whereas for one your maximum power point is somewhere here, for the second one it is probably somewhere here, for the third one it is probably somewhere there, something like that. For each of them that fill factor, which will be the ratio in all of them, in all these cases your denominator for the fill factor is this. So, in all these cases denominator is starting off with a product corresponding to the coordinates of this point, numerator is here for this, numerator is here for this, numerator is here for this. Okay. So, numerator can be dramatically less as you go from 1 to 2 to 3, denominator is the same. So, the fill factor is totally different. Okay. So, the fill factor is very different for these cases, and therefore, if you simply do this thing that this idea, you stick to this idea that you go to a shop and or you go to some online location and you want to buy this solar panel, and you simply look at open circuit potential saying, oh, what is the open circuit voltage, I want a 5 volt solar panel, and there are like half a dozen manufacturers giving you a 5 volt solar panel. Let us say some panel with multiple cells in it is some 5 volts, and you want a 5 volt panel, and there are multiple people selling a 5 volt panel, and you simply go buy the cheapest one, right. So, when you do that, you have to bear in mind that you are missing this point, that each of those 5 panels potentially could have different fill factors. Maybe they are the same, we do not know, maybe it is the same thing being sold more expensively in one place and less expensively in another place, that is also possible. But the point is there is a good chance that these fill factors may be different, and it is important for you to know what is that fill factor. So, you need this curve, or you need at least this data from them saying what is the fill factor, and then on that basis only you should make your judgment. So, the closer it is to 1, that is the value that you should be more interested in. Okay. And just a couple more points related to this which will help us sort of get a more complete picture on this, is that we can also look at the idea that what is given that you have this equation relationship between load current and the load voltage. What happens to this solar panel as let us say a cloud passes by, or there is some change in the amount of sunlight that is falling on the solar panel? How is the solar panel's behavior changing, right? So, when you want to do that, when you look at that carefully, what we see is that the photocurrent depends pretty much on the sunlight, because that is the source of the current. So, how much sunlight falls, if twice as much sunlight falls, you can expect twice as much current to come, sort of, you can expect that it will depend linearly on the amount of sunlight that is coming. So, if you let us say you decrease by some percentage, this will keep decreasing correspondingly, the amount of photocurrent. But if you look at the open circuit voltage and you look at its relationship to the photocurrent, okay, if you look at this relationship, it is a logarithmic relationship, there is a ln there. Okay. So, if you take again 2.303 log, let us say 2.303 log, so let us convert that from natural log to log to the base 10, if you keep that in mind. So, then and let us say for a moment, just for understanding sake, let us ignore the 1, ignore the 1 for the moment. What this means is, if the current drops from say by a factor of 100, something that was say, just to give some 100 amps, it drops to 1 amp, because you have taken a log, that is basically a change of a factor of 2 orders of magnitude, right. So, 2 is what it is. So, something current changes by 100, voltage changes by 2, that factor that impacts the voltage changes by 2. So, what it means is, even though you may have dramatic changes in current, the open circuit potential is much less affected by it. Okay. So, the effect of the incoming sunlight, which affects the photocurrents very significantly, affects the open circuit voltage much more mildly, and therefore, for the same variation in the sunlight, the voltage change is much more narrow. Current change is large, voltage change is narrow. So, voltage change is just this much. Okay. So, that whereas the current change is this much. So, that is again something that you have to keep in mind. So, a solar cell behaves very differently. So, I mean, or differently from what we intuitively think it might do. Okay. So, at least this thing, or at least we may be unaware that it is doing all these things, this is what it is doing. So, again you have to look at the fact that there are peak power points. So, you will have some peak power point here corresponding to this, some other peak power point here, some other peak power point here. So, you have to keep track of this peak power point and accordingly use it. Okay. So, in fact, they even have maximum power point trackers. They have circuits which keep track of this maximum power point and try to optimize the the way the external circuit is working with respect to this solar panel to track this maximum power point and use the best use of it. Okay. So, therefore, this is important stuff. So, we cannot ignore it, that is my point. So, you have to, and people who manufacture these kinds of things, who are trying to make the best use of the solar panels, are looking into all these issues. So, that is how this is used. So, I would just like to finish off with a couple of comments here. One is and that is first got to do with the aging. So, you put a solar panel out there, again you look at the open circuit. So, you put it brand new, it will have some open circuit, after many years of operation it will have some open circuit, you will find that that does not change much. So, again this is again an instance where you have to understand that the open circuit voltage does not fully capture the complexity of the operation of the solar panel, right. So, what is happening in general, for the solar panel to operate well, you want the shunt resistor to be as high as possible, the series resistor to be as low as possible. So, RS should be low, RSH should be high. If you do that, the current going down this path will be very low, the current going down this path will be higher, and therefore, and if RS is low, the voltage across your load will be high. Okay. So, therefore, you want this to be true, you want this to be true, you want this to be true. Generally what happens is, over a period of time impurities will diffuse into the solar panel, and as a result RSH will start decreasing. So, this will start decreasing and RS will start increasing. So, how does that affect us? When you go to very high currents in the circuit, then your impact of RS starts showing up more. So, RS starts impacting us here. So, this is where the RS impact is beginning to impact us. So, increase in RS starts impacting us, because higher currents in the higher current region you are adding more IR drop. So, correspondingly what you get out of the panel becomes less. On the other hand, the shunt resistor starts impacting us in the high voltage region, and so in the high voltage region again your ability to get power out of the solar panel decreases dramatically as your shunt resistor starts becoming lower and lower in value, because you are now giving an alternate path for the current. So, you can see here the characteristic is going to change dramatically, and therefore, it is also going to affect your maximum power point. Okay. So, even though open circuit voltage will look relatively undisturbed. So, this is again important information to keep in mind, that this is how the character of the solar panel is changing with time, and you have to keep that in mind when you use that panel. Okay. So, so these are all the major parameters associated. So, just to sum up, the solar cell is a current source. So, that is one point that we would like to remember. The IV relationship is complicated. Incidentally, in this context I will also point out that in the IV relationship we did not see the band gap, EG did not show up in that relationship, and that is primarily for two reasons, because the EG sorts the band gap sort of sets the upper limit for what you can get as the open circuit voltage, but since you have all these other events going on like recombination etc., it is not directly impacting your voltage. And also we are looking at the characteristic of this cell from an external perspective of load voltage, diode voltage etc. So, our approach also puts us in a situation where we are not necessarily directly tapping into the exact value of the band gap into that equation itself. But basically it sets a sort of an upper limit, but it does not show up in the equation. So, that is the point we have to remember. So, but also I have also highlighted that the IV relationship is complicated. So, most importantly, the OCV is not the most important parameter that you have to that reflects the capability of the solar panel. That is not the most important parameter, although because we are used to this idea from various other buying batteries etc., we tend to go there and ask for voltage with respect to the voltage. Rather, the fill factor of the solar cell is the most important parameter. That is what decides how well the solar cell can function. And not just that, if you know the fill factor and you know the IV characteristic, you should try your best to operate at the maximum power point. And as I said, there are people who set up circuits called the maximum power point tracker to keep track of the maximum power point and keep the load on that solar panel corresponding to that, so that you are fully benefiting from that solar panel. And so, that is what I have said here, the solar cell must be coupled with an end use that uses the maximum power point. Okay. So, those are the important ideas that we discussed today, where we basically took all the learning that we have had so far and tried to put together the thoughts, the ideas and the equations that relate to how the solar panel actually gets used and also try to understand how its characteristics impact the end use, what care we must take in the end use to fully benefit from the solar cell. Okay. Thank you.